There's our Dalton. Okay, for Dalton's is done there. For Avogadro's, how many liters of nitrogen did you calculate? .01. Is it .01? Did anybody else get .01? And so that means it's .01 liters of nitrogen, 99.99 liters of oxygen. Is that correct? Oh, .01. .01, it could be, yeah, .01 liters of nitrogen and .99 liters would give us a total of 1. Is that what other people got? Oh, on the moles? No. Moles and volume, they're proportional to each other, but you know, 1 mole is, under normal conditions, is 24.45 liters. Okay, so we have 0.01 moles of nitrogen, but the pressure is 186. Temperature is okay, 25 degrees C. It's not. And so how many liters of nitrogen? Well, what can you tell me about this? This is going to be some liters of nitrogen. I can tell you what the pressure is going to be easily. What is the pressure going to be? 279. And so how many liters of nitrogen is that to give me a 279 millimeters of mercury? Maybe this is too advanced. You know, this mixture, what is the percent nitrogen in this mixture? How would I figure out the percent nitrogen in this mixture? The percent nitrogen, I would take this. I would take 186 divided by 279. You know what that's called? That's called the pressure fraction. If I take the pressure fraction and multiply it by 100%, that should give me my percent. You know, the total is 279. Out of that 279, how much is nitrogen? 186. So 186 parts out of 279 times 100% gives me what? 66.7? 66.7% nitrogen. All right, the percent oxygen is going to be the balance, which should be 33.3, or we could calculate it. The percent oxygen is going to be 93 parts out of 279, or oxygen times 100%, and it should come out, what does it come out to? It should come out to 33.3 because both of these have to add up to 100%. And so 186 plus 93 is going to give us 100% of the total. Okay, so how many liters? Well, how many liters total mixture do I have? 1 liter. Out of that 1 liter, what percentage is nitrogen? 66.7. So this is going to be 0.7 liters of nitrogen, or 0.67 liters, or 0.667 liters of nitrogen. I'm just going to keep the numbers simple. 0.7 liters of nitrogen at 279, and so this has got to be 0.3. Or 0.333. So there's going to be 0.3 liters of oxygen at 279 millimeters of Hg. And this is going to give me, well, 0.7 plus 0.3 is going to give me 1 liter. So I'm going to end up with 1 liter of mix, and the pressure is going to be 279 liters of Hg. And so 0.7 liters of nitrogen plus 0.3 liters of oxygen gives us 1 liter of mixture. However, 279 millimeters of mercury plus 279 millimeters of mercury gives us 279 millimeters of mercury. All right, this is advanced, probably advanced level. But don't worry about that second confirmation. Yeah, but I just want to emphasize 2 ways of looking at mixtures. How you look at a mixture depends on what's easiest. So here we got some KClO3. What's KClO3 called? Potassium chlorate. What chemical property of potassium chlorate stands out? If you're thinking about potassium chlorate, and what's the first or most significant chemical property that comes to mind for potassium chlorate? Redox, yeah, for sure. As far as metathesis goes, nothing stands out. Potassium ions are soluble, chloride ions are soluble. Metathesis is 0. Acid base, potassium ions, neither. Chloride ions are some of the weakest bases around. Chloride ions are like chloride. Chloride's not really much of a base. But redox really stands out. Why does redox stand out so much? Redox is because of the chlorine. The chlorine, what about the chlorine that makes it really stand out? Yeah, a +5 charge, which means it's very reactive as a oxidizer or very reactive as a reducer. Yeah, and so it turns out potassium chlorate is unstable. It's a powerful oxidizer. Usually you want to feed oxidizers. You want to feed them reducers, right? But this oxidizer is so hungry, you know what it does? It cannibalizes itself. It's going to feed off itself because it's going to take the electrons off what? What can it take electrons off? It's going to cannibalize itself. Well, is it going to take it from the potassium ions? If the chlorine's hungry for electrons, it's going to feed off itself. What is it going to feed off? The potassium ions or the oxygens? The oxygens. Unfortunately, this is going to, well, it doesn't happen easily. We have to get some temperature in there. Delta, this triangle means heated up. So that's what the burner is there for. You start heating it up, and you know what happens? That chlorine takes electrons from oxygen. And we went from +5 to, what's the chlorine here in KCl? -1, and the oxygens are going to be left with no electrons. Well, no extra electrons, and we're going to be left with oxygen gas. KCl is very stable here, so the chlorine ended up taking the electrons from the oxygens in chlorate. And the chlorate's not that stable. Well, what can we use this reaction for? We can use this reaction to generate oxygen. So we heat the potassium chlorate, you're going to generate oxygen. Is KCl a gas? No, KCl is a solid. Potassium chlorate's a solid. And so what we should get is we should get pure oxygen gas. The decomposition of KClO3 is going to give us pure oxygen gas. And we can capture that. One of the easiest ways of capturing a gas is by doing it underwater, like this. And so if you fill up this tube full of water, so there's no gas in the tube, and so we have this is called a gas collection tube. to fill that up with water, like this, and then cap it, and then flip it upside down. Flip it upside down, and then submerge it in water like this. This whole tube would be filled with water. And then what you can do is you can bubble your oxygen in here. And as the oxygen rises, it's going to push the water level down. And in this way, there's no air contaminating our oxygen, because this was originally all water. So yeah, that's a great idea for collecting pure oxygen, but unfortunately the oxygen is not pure. What's contaminating our oxygen? Do you know what would be contaminating our oxygen?
Wasn't there like air in the tubes, not vacuum?
No. Well, yeah, there'd be air in here, right? There'd be air. But what you do is this. You start this and bubble out the air first. Once you're sure you've purged all the air out, then you move your tube over this to collect it. And so what we do first is we purge the system of air and then start collecting the gas. There's going to be a delay, so we're going to waste some oxygen, but it beats having to purify oxygen. You know, how do you get the air impurity out of the oxygen? That's not easy to do. So there's no air contaminating it if we do this correctly. What is contaminating it? What is contaminating it is like, have you ever had a fish bowl, or have you been into the indoor swimming pool over here? If you have a fish bowl or you've been into the indoor swimming pool, let's say if you shrank down and go inside here, you're going to notice something about the air in here. The air in here is going to be very humid. Like indoor swimming pool, the air inside indoor swimming pool is very humid. And that is, if you're bubbling oxygen in the water, the oxygen is going to be saturated with water vapor, humidity. And so what happens is that the oxygen is contaminated with water vapor. When we collect gases like this, we end up getting 100% relative humidity. Is the air in this room at 100% relative humidity? No. But if you have a lot of water in a little room, then it is going to be at 100% relative humidity. If you have a little bit of water in a big room, then we're okay. You know, all this can evaporate, no problem. But what's going to happen is the water is going to keep evaporating off this or vaporizing off this, and pretty soon this thing is going to be saturated with water vapor. And so if you had to live in here, it'd be very humid. So we aren't collecting pure oxygen, we're collecting an oxygen-water mix. If we're collecting an oxygen-water mix, how much of this volume is oxygen? How much of this volume is water vapor? And so we have O2 gas and H2O gas. And so let's say I collected 1 liter of this gas mixture. Out of that 1 liter, how many liters is pure oxygen? How many liters is pure water? Now, is that an easy way to visualize this mixture? No, that's not. And so probably an easier way to visualize this mixture, let's say I did have 1 liter, an easier way of visualizing it is like this. If I had 1 atmosphere of gas in here, how many atmospheres of oxygen, how many atmospheres of water vapor? Well, that's just as difficult. That's just as difficult, except for this. The volume changes depending on the size of the container. You know, if you have a bigger container, you got more liters of water. A smaller container, less liters of water vapor, right? But it turns out the pressure does not change. It doesn't matter how big or how small this container is, it's going to get saturated with water vapor. Let's say this is the water vapor. So it gets saturated with water vapor, and then we have our oxygen in here. I think probably too much water vapor. But And so what happens is this. When water evaporates off here, we call it vaporization or evaporation. And so the water is going to evaporate off. And then it's going to saturate the container. What saturating the container means is that you generate enough water particles or water molecules in the gas that what happens is they come back down and strike the surface. As they come back down and strike the surface, that's the opposite of evaporation or vaporization, which is called condensation. So initially condensation is pretty slow because there's not much water vapor there. But pretty soon the condensation rate speeds up because the more water molecules you have in there, the more collisions with the surface. The more collisions with the surface, the more of those water molecules get stuck back into the liquid phase. And eventually you'll reach this point where you'll evaporate 5 water molecules, but you'll condense 5 water molecules at the same time. And so when that happens, we call it equilibrium. That is 5 water molecules. For every 5 water molecules that vaporize, 5 water molecules condense. It's equilibrium. Equilibrium means that there is no change. No change. So the net change is 0. 5 evaporate, 5 condense. But we call it dynamic. Dynamic means there is change. Equilibrium means there's no change. And this is called a dynamic equilibrium. There's change, but there's no change. So how can you have change but no change? Dynamic, change. Equilibrium, no change. How can you have change but no change? This is how you can have it. How you can have it is there's no change. The amount of liquid stays the same. The amount of gaseous water stays the same. So that's equilibrium. The dynamic comes by looking at the individual molecules. So the molecules never stop evaporating. Can you tell water to stop evaporating? Can anybody tell water to stop evaporating? No, if it's at a certain temperature, it's going to stop. It's going to continue. And so the water will never stop evaporating. And the water will never stop condensing, the water vapor. It just so happens that they're matched. So I have 3 water molecules vaporizing. At the same time, 3 molecules are condensing. So 3 vaporize, 3 condense. So nothing's changing. But it's changing. It's changing because the water molecules are constantly cycling back and forth. Well, if I have a bigger container, it doesn't matter. If I have a bigger container, yeah, then I can fill it with more water molecules, but I'm going to hit the same dynamic equilibrium. In other words, no matter what the size of the container, the pressure of the water molecules will stay fixed. The volume of the water molecules will change. And so it's much easier to do this as a Dalton's mixture than as a Avogadro's mixture. In fact, it's easy to measure how much water gets vaporized just by doing some simple experimental measurements. And so this is called the vapor pressure of water. The vapor pressure of water is the pressure that's generated by the water vapor at different temperatures. And so if we go to room temperature here, 25.0 degrees C, the vapor pressure of water is 23.834 millimeters of mercury. And so if I'm at 25 degrees C, I'm going to have 23.8 millimeters of mercury of water vapor pressure, so the collisions. It could be a bigger container or a small container, I'm still going to get the same number of collisions per unit area. Now, if I increase the temperature to 26, then I go up to 25.3. If I decrease the temperature to 24, I go down to 22.4. And so the water vapor vapor pressure changes with temperature. And so the higher the temperature, the more water molecules I'm gonna vaporize, and that's gonna increase the condensation rate, and eventually we can balance again, but I'm gonna end up with a net more water molecules here. If I cool it down, I'm gonna lower this, and I'll hit that dynamic equilibrium over here. And so this chart is for what we call a 100% relative humidity. The water has to be saturated in order to generate this. I mean, the water, not the water, the gas has to be saturated with water vapor in order to generate these pressures here. Okay, I'm gonna stop here. I'm still in the middle of this, but we'll continue this after the break.